Wonderful, thank you. And thanks for the opportunity to speak at the summer school. I'm delighted to be here. Before starting in the lecture, I guess some kind of housekeeping notes. So first of all, let me recopy all of this into the chat for people who are just joining. Here is a Jamboard link. So I plan to give this lectures over Jamboard. I'll share the screen, so you should be able to just watch over Zoom, but if you prefer, you can also open the Jamboard, which means you'll be able to scroll backwards and forward through the slides if you want to go back to a previous page or whatever. I also wanted to share notes. Let me see. Oh, except now I can't copy anymore. I seem to be having minor technical difficulties here. Maybe somebody else would be able to recopy and paste the two links I just gave in the chat.
I think do we have do you have
oh, here we go. Sorry, there was the problem. So let me recopy. Here is, first of all, this is a review package. No, does that not work? I see. I seem to be opening it instead of copying and pasting it.
You can copy it from the URL line.
Oh yeah, maybe that would work. Here, so let me see. Here is two links for me to share. The first is a review package on the cohomology of groups, which is something prepared for a summer school, a different summer school last year, which Peter and I wanted to share for anybody who wants a little bit more background on these topics around things like virtual cohomological dimension and Bier-Ekman duality groups, virtual duality groups, these concepts. I think our plan is to effectively black box the properties of these terms that we'll use, but if anybody's serious about learning all this material, then definitely those exercises are recommended. And then the second link is for the notes, or at least the current draft of the notes and exercises for our lectures. And we'll continue to update that, that link as we revise the lectures as the week progresses. Okay, great. So anyways, those are the links. And right on that point, I guess we can begin. Yes, folks are here?
Yes.
Okay, awesome, great. So let us begin with this. First page is, I'm going to do a review of the key points from Peter's lecture from this morning. The object of my 3 lectures is going to be to say something about the top degree cohomology of SLN R when R is a Euclidean domain. Okay, and so today I'd like to fix the following notation. R is a ring throughout, and throughout F is always going to be its field of fractions. And I'm really interested in the situation where R is the ring of integers in some number field F. So throughout today's talks, we'll stick with this convention. F is a number field, R is its ring of integers. Really the most important example being the case where F is the rational numbers and R is the integers. That's the key example. All right, so a quick review from Peter's lectures. Okay, and I should say that although I think Peter focused on the case that R is the integers, in fact, all of his results hold more generally for a number ring R. Okay, so first of all, recall that it's a theorem of Borel and Serre that the virtual cohomological dimension, this is this quantity Peter denoted by nu in the statement of duality.
I didn't get to duality groups. I didn't define duality groups in general. I'd only wrote down Borel-Serre duality for Z.
Great. Perfect. That's right. If folks are interested in more background, take a look at that review package on cohomology of groups. Okay, great. So that quantity nu has a name. It's called the virtual cohomological dimension. This actually means something a little more general, which you can look up in this review package if you're interested. But I guess for our purposes, this is this quantity that is going to appear in the statement of Borel-Serre duality. And here is a formula given a number ring R. Here's a formula for the virtual cohomological dimension of SLN R. And really, just what I want us to take away from this formula, I'm not interested in the details. What we can take away from this is first of all, this quantity is known. It is quadratic in N. It somehow depends on the Galois theory of F. It depends on the number of real and complex embeddings of F. And right, notably, it is an upper bound on the degrees where we can have non-zero cohomology for the group SLNR if we take coefficients in a rational representation. Okay, so that's the VCD, which I'll denote VCD. Peter called it nu, I believe. And Peter stated this Borel-Serre duality. It's an example of virtual Beer-Ekman duality for these groups. So SLNR is a what's called a virtual duality group. Its dualizing module is called the Steinberg Module. And what that means is that the following formula holds. Okay, so what that means is that we have this, this duality statement that you can view as a twisted form of Poincaré duality. It says that the codimension I cohomology of SLNR with coefficients in a rational representation is isomorphic to the degree I homology with coefficients in, but now I need to tensor my representation V with the Steinberg module. Okay, and this holds for all rational SLNR representations. So the upshot is that if, as we are in this lecture series, interested in studying the high degree cohomology of these groups, then we can instead study the low degree homology of the groups, but at the expense of twisting our coefficient systems by this Steinberg representation. All right. And a reminder, so I believe Peter defined the Steinberg representation and defined it in terms of these Tietz buildings. So he talked about the Borel-Serre bordification of the symmetric space. Let me just say that the Tietz building, for the purposes of my talks, is going to be a simplicial complex, an abstract simplicial complex, where the vertices are indexed by subspaces of f to the n, non-zero proper subspaces, and a simplex in my Tietz building corresponds to a flag of subspaces. Okay, so a collection of vertices spans a simplex if and only if they are a flag. Oh, is everything working? Sorry, I can see the screen.
Yeah.
Can you still see my Jamboard?
Yeah.
Oh, okay, great. Thank you. Good, good.
Something happened.
Give me a shout if I should pause. Great. So something Peter used in his lectures, I believe, is the Solomon-Tietz result that this Tietz building, topologically, is homotopy equivalent to a wedge of infinitely many spheres of dimension n-2. And we'll definitely use that result frequently as well. So one thing this tells us is that these Tietz buildings only have one non-vanishing reduced homology group, and this one reduced homology group is, by definition, the Steinberg module. So, right, the main takeaway from Peter's lecture, for the purposes of today's lecture, are this duality statement, and we now have some concept of what this value VCD is and what this Steinberg module is. Okay. So very broadly speaking, the motivating question for my lectures is the following, which is, what can we say about the largest cohomological degree Q, the function of n, with the property that SLNR has non-zero degree Q cohomology? Well, what is the largest degree where we have rational cohomology? And in general, for a general number ring R, this question is open. In fact, it's even open in the case where R is the integers. The VCD gives us an upper bound on what this quantity can be, but lower bounds are right now. And a conjecture that I believe Peter cited due to Church, Farb, Putman is the following. They conjectured that if we take n at least I plus 2, and we take here just trivial coefficients, rational coefficients, untwisted, then the degree I cohomology of SLN Z, so R is the integers here, then this vanishes for n sufficiently large. Okay, and this, so right now this is conjectural. In a moment I'll say something about what's known, but I will point out that this conjecture naturally raises the corresponding questions. This conjecture was made for the integers, but you could ask the same question for any number ring. Okay, do you get vanishing in those high degrees? Okay, so next I'm going to turn the page on this Jamboard, and this table is a summary of what's currently known about these questions. I'm going to go just very quickly over this because it's not a focus of my lecture, and in fact it's something that Peter's going to talk about in depth at a later point in the lecture series. So right now this is just a very quick teaser, but let me point out that the first question of what happens in the VCD if we choose our number ring R, what can we say about the cohomology with trivial coefficients in Q in that top degree where you could possibly have non-vanishing cohomology? And what's known, it's a result of Leon-Charba from the 70s, that if R is, a Euclidean ring, then in fact these groups vanish in the top degrees. So that, among other things, establishes the I equals 0 case of the Church, Farb, Putman conjectures. Church, Farb, Putman proved that if R is not a PID, then you have a non-vanishing result for this cohomology in the VCD. And in fact, they gave bounds on the dimension in terms of the class number of the ring R. And there's some partial results known in the case, in a handful of the known examples of rings that are PIDs but not Euclidean domains. There are some non-vanishing results known. I think Peter will elaborate on this in his talks. Okay, so we could still ask the question, maybe the Church, Farb, Putman conjectures hold, and maybe they hold for all Euclidean rings, maybe. And there's a little bit more evidence in favor of this, which is the following. It's known for both the integers and for these two other Euclidean rings, Euclidean number rings, that you have vanishing in a suitable range in the codimension 1 case, in this box here. And then just as of a month ago or so, it is known that in the case of the integers, we also have vanishing in the codimension 2 case for the integers. Okay. And so, right, this is the state of knowledge. And I hope that maybe everyone here might be a little bit interested in helping us figure out what happens in other rings and in other codimensions. Great. So let me, that was very, very fast survey of these results. So Peter will talk more about those in a few talks. But now, let us get down to business at the point of today's lectures. Okay, so let me remind us the meta goal. Am I writing large enough for this to be visible in the classroom?
Yes. Yeah.
Yeah, okay, great. So the meta goal is to understand these cohomology groups of SL and R is a number ring, rational trivial coefficients for Q large. I guess that wasn't a question. And the goal of my lectures is going to be specifically to prove this result of Lee-Sharba which stated that if you look at the very top dimensional cohomology groups, if you look in the VCD, that top degree where you could possibly have non-vanishing cohomology, then in fact these groups vanish if R is Euclidean. Okay, so that is the goal of my 3 lectures, and although we're doing this just for the very top degree, I'm using proofs that are not the original proofs due to Lee-Sharba, but instead we'll use some slightly more modern proof of this result, and the reason for that is that the hope is that this will showcase some of the methods that were used in the other results in the table that I just showed you. So we can view this, we're taking this as something of a warm-up case for the proofs in higher codimension. Okay, great. So let me remind us. So towards this goal, a reminder is that the duality statement in the case of trivial coefficients is the statement that the codimension I cohomology of our groups is isomorphic to the dimension I homology of the groups with coefficients in this rationalized Steinberg module. Okay, and what this means, and I mean what I'm about to say, you could take as like the definition of these groups if you wish. Although I encourage you, if this seems unfamiliar, to take a look at those that review package on cohomology of groups. So to compute these groups, one approach we could take is to take a resolution of our coefficient systems by flat Q, S, L, and R modules. I'm just writing down one of the definitions of the, how to compute the Tor functor. From there, we can take S, L, and R covariance of the terms in this resolution, and then take homology of the resulting chain complex. Okay, and that these homology groups, these groups will be exactly the I homology group resulting from this construction is going to be exactly this codimension I cohomology group of SLNR. And as a reminder, let me say, so reminder that by coinvariance, if I have a group G acting on V, then coinvariants are by definition the largest quotient with trivial G action. So I can mod out by the action of G as follows. Okay. Great. Okay. Again, just from the definition of group homology as a, an instance of the Tor functor, this is one of the ways that we can compute these homology groups. And the upshot of that is that one of the approaches to this whole program is to try to come up with nice resolutions for this Steinberg module. And when I say nice, I mean somehow small enough that we actually have a hope of being able to understand the coinvariance.
So the Steinberg module is finitely generated as an SLNR module?
Yes, yes. So
I guess we don't only know that for Euclidean.
Thank you.
For Euclidean rings.
All right. So our goal to compute these high-degree cohomology groups has now become the problem of understanding or being able to compute nice resolutions, or at least partial resolutions, of this Steinberg module. And then the key to do that is to understand the topology of this Tietz building. So we're going to do that using simplicial methods by studying the Tietz building and associated simplicial complexes. Okay. And I'll also comment, there is one of the exercises, one of the guided exercises that's in our lecture package is a construction of the resolution due to Lee and Sharba, which is fondly called the Sharbley resolution. So there's a whole kind of guided proof of how to construct this resolution. Though unfortunately, it seems that this particular resolution is somehow too big to perform computations of coinvariance past the codimension 0, past the very first degree. And so in these lectures, we'll talk about an alternate approach to this whole program. Okay. Great. So maybe I'll pause here for a moment before we kind of get started with the actual content of the proof. Are there any questions?
Seems not.
Oh, right. Okay, well, let's go. Then, okay, so today we want to prove this Lee-Sharba result that when R is Euclidean, we get vanishing of the cohomology of SLNR in the top degree, in the BCD. So let's assume for the rest of the lecture that R is Euclidean. Okay. again, are to putting a number ring, and F is going to be its field of fractions. And, right, if we remember what this, well, I mean, you could understand this from the 3 bullet points I just wrote, but also let me just remind us directly that if we want to understand the top degree homology of SLNR, then by duality, that is the 0th degree homology of SLNR with coefficients in the rational Steinberg module. And that is precisely the coinvariance of this rationalized Steinberg module with respect to the SLNR action. Okay, and so our strategy is going to be to try to find a generating set for this Steinberg module where it's clear that the generators vanish when we take coinvariance. And if we can do that, we're done. If we can do that, that shows these coinvariants vanish, and then that proves vanishing of this top degree cohomology group. So the strategy is to find generators of, in fact, same with well, let me put it this way. Find generators of the rationalized Steinberg module that vanish in coinvariance. Okay. So let's start as a warm-up considering the case n equals 2. In this case, our teach building, by definition, it's just a discrete set. It is the set of lines in F2. And the Steinberg module is the reduced 0th homology, by definition. So this is generated by all differences of lines. They're just, so I'm now treating these lines as just formal symbols in this group, and this is the group on formal differences of lines in F2. Okay, so very concretely, here's an example of, in the case R equals Z, here's an element in the Steinberg module. It is the difference in the formal symbols that are the lines, the x-axis and the y-axis. Okay, and observe the following. So we look like we're in luck because if we consider the matrix G in SL2Z as follows, this is a matrix that swaps these two lines. And I've added a negative sign here just to make sure the determinant is 1. So it doesn't fix the lines, or I mean it swaps one to the negative of the other. But that's fine. We're just interested in the action on lines as sets. Okay, so this is a matrix that interchanges my two coordinate axes. And so when I act by this matrix on this abelian group, this has the effect of negating x, negating this element x. And that's great because that means that this element x is going to have to vanish when we take coinvariance, since we're working rationally. Okay, so x vanishes when we take coinvariance. Great, good news. So it seems like we're in luck. So far, so good. We have a generating set. We've chosen one generator, and we've established that that particular generator vanishes in coinvariance. So if we were naive, maybe we would hope that we could, in fact, perform the same trick for all of these generators, and maybe we'd just be done. And unfortunately, it's not quite that easy. So let's go on to the next page. Let's consider another example of a generator. Again, this is R is the integers. But now let's consider, the generator Y, given by the difference in the x-axis and this other line, this line spanned by the vector 1, 2. And I'm going to leave it as an exercise to check that there is no element of SL2Z that swaps those two lines. All right. And somehow the problem is, what has gone wrong here? The problem is that if I intersect these two lines with just the integer lattice, I look at the integer points on these two lines, and I take bases for those two abelian subgroups. In fact, here, these are, so for example, I need a choice of primitive vectors over the integers for these two lines. Here's such a choice. If I choose these two primitive vectors, these are not a basis for Z2. So this is the problem. This is not a basis for Z2. Say they span an index 2 subgroup. Okay, and I can see that because if I make these the columns of a matrix, that matrix has determinant 2. Okay, the upshot is that, written out, that if I look at what happens when I intersect these two lines, with Z2, right, then unfortunately they don't give me everything. It's an index 2 subgroup. And that's why this scheme falls apart. Okay, so unfortunately, it's not immediately clear that all of these generators are going to vanish when we take coinvariance. But the key claim is that, in fact, all of these generators for the Steinberg module can be written as linear combinations of those generators that have these nice integrality properties, that have this determinant 1 property that we needed in order to perform this trick. So the key claim is when R is Euclidean, then this Steinberg module, let me just, I'll write it just for 2 at this point, is generated by this subset of lines with this property that they come from a basis for Z2 and not just for R2 and not just for F2. So, right, in other words, L1 is FB1 and L2 is FB2 for some basis for R2, B1, B2. Okay. And what that means is that we actually can use this trick. if we have a pair of lines with this property, then you can find a matrix G, just like we did on the previous page, that swaps those two lines, and then it's clear that this generator vanishes in coinvariance. Okay. So it's an exercise. I will leave it to everyone. I will leave it, to you all as an exercise to see if you can write this particular difference of lines as a linear combination of differences of lines where they all pairwise have this nice integrality property, this determinant 1 property. Exercise. All right, so let's talk about the case of general N. Okay. So for general n greater than or equal to 2, here's the situation. First, we need to understand what the Steinberg module is. We need some generating set for the Steinberg module. And in that direction, here's a definition. Given a frame for Fn, so a frame is a decomposition of my vector space as a direct sum of lines. Given a frame for Fn, here's some notation. I'm going to let S of this collection of lines be a subcomplex of my Teach building. This is the subcomplex of all simplices that on vertices indexed by all, I guess, proper, or all sums, all direct sums of subsets of this collection of lines. They have to be proper non-empty subsets. All right. This is called an apartment. Okay, so let's draw a picture of what an apartment looks like. For example, when n equals 3, then we have the following picture. We have a circle. Okay, so this is, I have my frame L1, L2, L3, and this is exactly the subcomplex of the Teach building that I get by taking all simplices on all vertices corresponding to sums of those 3 lines. It's a circle, okay? And in general, it's going to be an n-2 sphere. So here's some exercises for you to check. The first is that these apartments are always going to be, in fact, homeomorphic to a sphere of dimension n-2. And I think the key observation is simplicity you can identify them with the barycentric subdivision of the boundary of an n-1 simplex, just in the way this picture here, this is the subdivision of the boundary of a triangle, where I have my lines as the vertex set of the triangle, and then every face I get the corresponding sum of those lines. But I can't take the sum of all n of them because the Tietz building only consists of proper vector spaces, subspaces. Okay, so that's an exercise. And part 2 of this exercise is to check that if we order the lines, in fact, we only need to order them up to even permutations, we obtain an orientation on the sphere. And if we have an orientation on the sphere, then we have, for that sphere, a well-defined fundamental class. And so that means that we can use these spheres to construct degree n minus 2 homology classes in our Tietz building. So the image of one of these apartments, the image of its fundamental class in degree n minus 2 homology, which makes sense, that fundamental class is well-defined even up to sign, given this order on the lines. The image of that fundamental class gives me an element of the Steinberg module. It gives me an element in degree n minus 2 homology. Okay, so the inclusion of one of these spheres in the Tietz building gives a homology class which I'll denote using brackets. And to make sense, again, to make sense of the sign of this class, I need to order those lines. And this is called an apartment class. Okay, great. And so let me turn the page for us. It is a theorem of Solomon and Tietz. That the Steinberg module, which we remember is this reduced degree n minus 2 homology, is generated by apartment classes. And this is for any R. This is without this assumption that R is Euclidean. And so, importantly, for generalizing this proof strategy that we talked about in the case when n equals 2, is this result of Ash and Rudolph, which says when R is Euclidean, when R is a Euclidean ring, then the Steinberg module is in fact generated by integral apartment classes, by which I mean those apartment classes that come from a basis for R to the n and not just the field. They have that integrality condition, which we can express like this. Which is to say, it comes from a basis for Rn and not just Fn. Okay. And the claim is that this means, in the case when R is Euclidean, we can use precisely that trick that we used earlier to to show that we can directly find an element in SLN-R that negates each of these generators, each of these integral apartment class generators, and that will directly show that our cohomology vanishes in the VCD. Okay, so we're now almost done, at least assuming this result of Ash-Rudolph. We're almost done our proof of Lee-Sharba, showing vanishing of SLNR in its VCD, the vanishing of that cohomology, rational cohomology group in the VCD. So here's the proof of Lee-Sharba, assuming this result about generation by integral apartment classes. Okay. So it suffices to show actually let me back up. So let me remind us. We're trying to show that these groups are 0. And we know that these groups are equal to the coinvariance of our Steinberg module. Okay. And we now know that this is generated by integral apartment classes. So it suffices to show that the integral apartment classes vanish in coinvariance. All right. And so let's check that. We can use precisely the mode of argument that we did in the n=2 case. Okay, so let's choose an integral frame. Okay, this means that if I choose a primitive vector over Rn for each of these lines, those primitive vectors have determinant 1. Okay, and then we'll do the same thing. G, sorry, let me back up. Sorry, i.e. Li is fbi for some basis. For Rn. Okay, we can do the same thing as before. Let's let G be this matrix. This matrix in SLNR written with respect to the basis V1 up to Vn. Okay. So notice that this has this property that it's going to send the line L1 to L2. It's going to send the line L2 to L1. And then it's going to fix every subsequent line. Okay. And what this means is that G is going to act on this collection of lines, just on this set of lines by an odd permutation. And what that means is it's going to act by an orientation reversing action on the sphere that is the corresponding apartment class. So it is going to negate the apartment class corresponding to this frame. And that's exactly what we wanted in order to ensure that it vanishes in coinvariance. Okay, so this gives an orientation reversing, I have a bit of trouble writing here, reversing action on the apartment class. Okay. And so what that means is that it's going to negate on, oh, sorry, I just mean on the apartment, on the actual sphere. So it's going to negate the apartment class. It stabilizes the sphere, but reverses its orientation. So let me draw this picture again of, just to remind us what this looks like. So here, L1, L2, L3, and then I have the three sums. So what happens, G, this matrix G is going to act by a reflection of this. Okay, G acts by a reflection. And so it negates the fundamental class of the sphere. So what this means is that the image of this apartment class vanishes in coinvariance. But because these integral apartment classes generate the Steinberg module per Asch-Rudolph result, because they generate the Steinberg module, this means that the Steinberg module, the rationalized Steinberg module, vanishes when we take coinvariance, and that's exactly what we wanted. So, write that down. Okay, great. And so that was it. That result was the goal for our lecture, this goal that these top degree cohomology groups vanish whenever R is Euclidean. And we've proven that that is true. This is a result originally due to Lee Sharba. We've proven that is true, assuming that this is chronological, because the Asch-Rudolph result is more recent. But we've proved that this holds, assuming this more recent result of Asch and Rudolph. And so the goal for the next lecture is to prove this theorem of Asch and Rudolph, which shows generation by integral apartment classes of the Steinberg module. And that will bring us a step closer to having a complete proof of this fact. Okay, so it's 10:15 a.m. in my time. Let us, I guess, stop here for our break.